So now I'm going to work through a few design problems involving lists. As always when I work through these problems, there's going to be some parts of it that are pretty familiar, things that you'll already know how to do. And then there'll be parts that are about the new list material. So what I recommend you do, and in fact I've said this before, I always recommend you do this, is get the starter file and work through it with me. And now in these problems, you might even try stopping the video for a bit and working ahead, and then starting the video and comparing what you did to what I did. Again, that's always a good idea. But don't worry about it if you get stuck and you need to start the video. After all, these are really the first list design problems that I've asked you to do. So you should expect it to take some time to master this new part of the recipe. There's a three-part problem here, having to do with all the owls in the owlery. First, there's a data definition problem where we need to design a data definition to represent the weights of all the owls. And then we're going to design two functions that operate on that data. As I go through this, and really whenever you're working on a design problem, you should have a copy of the design recipe pages opened up and maybe off to the side next to your Dr. Racket window. So let me start first by dividing my file into two parts, one part for data definitions and one part for the functions. And now let's get to the data definition. Let's see, we're going to represent the weight of all the owls in the owlery. We don't know how many owls there's going to be. So we need arbitrary size data, so we need a well-formed self-referential data definition. Here we go. List of number is one of either empty, because that's the base case, or cons number on list of number. That's the self-reference case there. For the interpretation, we'll say that each number in the list is an owl weight, and with numbers it's always good to say the units, so we'll say that it's an owl weight in ounces. And let's see, we'll have a couple of examples. In one example, we always put the base case example first in the data examples. So we'll say ln 1 is empty, and ln 2, I don't know, let's make it too long, and one owl will weigh 60 ounces and the other owl will weigh 42 ounces. Now we'll do the template, fun for ln. Let's see, the first rule is one of, because there's two cases, so that gets us a con with two cases. The second rule is atomic distinct for empty, so that gets us the empty question mark predicate and ... in the answer. Next we've got compound, because a cons is a compound. It's a cons of a number, which is each element of the list is a number, and list of number, which is the self-reference. So in the template we take apart the cons. First of ln is just number, but rest of ln is self-reference, so the self-reference rule comes in. And we wrap rest of ln into a natural recursion, a call to the very same template function. We run it, there's no errors, so it's well formed. We comment out the template, there we go, we've got the complete data definition. And again, because there's arbitrary sized information, we need arbitrary sized data, so there's a well-formed self-referential type comment and a natural recursion in the template. Now let's go design the functions. Let's see, the first function is going to consume the weights of some owls and produce the total weight of all those owls. So let's see, it's going to consume list of number, because that's the type that we're using to represent the weights of an arbitrary number of owls. And it's going to produce, well, the weight of a number of owls is the sum of a bunch of numbers, so that's number. Produce total weight of owls in consumed list. So we take a bunch of owls, we produce the total weight. The stub is defined, let's call this function sum ln, and the stub will just produce 0. Call that the stub. Now let's do some examples. There's a rule that for functions operating on arbitrary sized data, the base case example should be first. So let's do that. Check expect sum of empty. Well, the sum of the weights in an empty list of weights is 0. Let's do another example. We'll do an example with just a single owl in it. So let's say the sum of maybe a list of owls that has a 160-ounce owl in it is what? Well, that's 60. And this might be a good place to be a little bit more elaborate about it. The reason it's 60 is because it's 60 plus the sum of all the owls in the rest of the list, which in this case is empty. So it's really 60 because it's 60 plus 0. Let's do one more. Sum of, let's see, cons 60, cons 42, and empty. Well, what's that going to be? Well, it's 60 plus the sum of the rest, which is 42, plus the sum of its rest, which is 0. You don't have to write that out like that, of course. You could just write it like this, because that's clearly what it is. But by writing it the other way, I'm starting to think out in my mind, well, how's this going to work? I'm always going to add the first weight to the total of all the other weights. Let me run those examples. They're well formed. I'll go and get the template. I bring the template down. I comment out the stub. I rename the template, and I'm especially careful to rename the natural recursion. Now let's see, the sum of an empty list of weights is 0. Otherwise, the sum of another list of weights, it looks like it's whatever the first weight is plus the sum of the remaining weights, or the sum of the rest of the list. So that's the first weight right there. In this first example, for example, that's going to be 60. And again, in this first example here, that whole natural recursion is going to be 0. Oh, so now I know what goes here. I just add these together. I add the first weight to the sum of the remaining weights. Let me get rid of these notes now. All tests pass. Notice what I did is I trusted the natural recursion, and I used the examples to help me think about what I did with the first item of the list and what I did with the result of the natural recursion. I don't ever let myself think about what I'm going to do with the rest of the list. What I think about is what I'm going to do with the result of the natural recursion. So there's that function done. Let's now do the second function, which is design a function that consumes the weights of owls and produces the total number of owls. Okay, so let's see. The signature is it consumes the weights of an arbitrary number of owls. So that's represented as list of number. And it produces how many weights there are in the list, or how many owls are represented. Well, that's not number. That's a natural number because it's 0, 1, or 2. It's something like that. So that's natural. Produce total number of weights in consumed list. We'll call this function count. There's the stub. Now let's do some examples. Again, there's a rule that the base case should be first, so check expect count. If I count the number of weights in an empty list of weights, that's 0. Now let's see, I could use the same examples as I used last time, or different ones. Let's use different ones. Check expect count, cons 12, empty. Well, how many weights are there in that list? Well, there's just 1, so I could just write 1. Or I could remind myself that the reason there's 1 is because there's 1 for the first weight in the list, the 12, and then there's 0 for the weights in the rest. So I could write it like that. Let's see, check, expect, count, cons 35, cons 12, empty. And here there's 1 for the 35. And then there's whatever's in the rest, which we already know is plus 1 and 0. So I can write that like that. I'll run it, and my tests are well formed. So let me go get the template. I'll copy the template down. Let me give myself a little more room to work here. I'll copy the template down. I'll comment out the stub. And then I'll rename the template and the natural recursion. Now let's see. If I'm trying to count how many weights there are in an empty list of weights, well, that test and just intuition tells me that that's 0. And now I'm trying to count the weights in a list that actually has elements in it. Well, the first weight, I don't really care what the first weight is. I just am counting the fact that there is a weight. So that's going to be replaced by just 1. That's what this is telling me here. In sum, we use the actual weight. So that stayed as first of ln. But in count, we're not using the actual weight. We're just using the existence of the weight. So we're going to put a 1 there. And now I'm going to deliberately make a mistake because I want to show you something about the too long lists rule. The mistake I'm going to make here is just make this be plus 1, and then I'll look at this and incorrectly decide to throw away the natural recursion and just put 0. And now I'll run it. And when I run it, this test is passing. It's only the test that's too long that's failing. And that's why we have that rule about having a test for lists that are too long. Because if you make a mistake throwing out the natural recursion, then your 1 long tests will often run properly. So now let me go back and pretend I didn't make that mistake. I'll close this. I'll just back up a little bit to where I was about to make that mistake. Here I was. And now I say to myself, well, I add 1, 2, and now what do? I trust the natural recursion. The natural recursion will be the right answer for the rest of the list, so I'm just going to trust it. I add 1 to whatever it produces. I run, and all 6 tests pass.